All right, looks like we have about half of our attendees now. We'll go ahead and get started with some of the introductory stuff here. Good evening, everyone. My name is Robert Haynes, and I'm with the National Weather Service in Burlington. I've now been doing these Skywarn presentations here virtually for about 5 years, so it's fun to think about how things have evolved over time. So what we'll be doing here tonight is we'll be discussing the Skywarn program and what it means to us, and we will go over some of the details on how you can observe and report thunderstorms and some of the damage that you might see in those situations. My name is, again, Robert Haynes, and welcome everyone to this presentation. Glad you could join us this evening. If there is any part of the presentation you miss, usually I take the best recording session and apply that on our YouTube channel. And if you haven't looked at the side panel through GoToWebinar, there is a question tab. And so I will be monitoring that from time to time, looking out for any questions from you. So let me know if you have any questions and I will answer them. There's a few areas in the presentation where we have breaks for questions, and at some point in the presentation, we'll give ourselves a 10-minute breaks to move off of our seat for a bit. All right, let's begin. So the presentation that we're going to discuss tonight is going to focus mostly on warm season type stuff. We'll discuss the basics of how Skywarn operates and how important it is to us at the National Weather Service. And with that, we'll discuss who we are at the National Weather Service here in Burlington, and then we'll dive right into the storm ingredients, storm types, and the National Weather Service's warning system, and how you can get the most out of that information. We'll then finish up with a little bit of stuff about safety and reporting severe weather. So this is who we are. We are the National Weather Service. We are a part of the federal government, and it is our duty to provide weather, water, and climate data with forecasts and warnings that help you make decisions that should protect your life and property, and as a side bonus, enhance the national economy. Our vision is to create a weather-ready nation. And so these presentations are part of how we accomplish that. So we can have a community that is prepared to respond to the various weather hazards of our region, including any water and climate dependent events as well. So we service here at the National Weather Service in Burlington. We cover not quite all of Vermont. We have every county except for Bennington and Windham. Bennington and Windham is going to be operated by the National Weather Service in Albany. But then we also have the 4 northernmost counties of northern New York here. So we serve an area that has a lot of complex terrain. And so with that, we have a lot of variable weather in our region. We have a lot of microclimates between all of our different valleys that are sandwiched between mountain ranges and lakes and broad river valleys as well. So we have a lot of unique weather in our region, but in a lot of ways, when it comes to severe type hazards, we have it pretty good. We don't have the destructive thunderstorm potential that a lot of the areas in the Western United States has. So this is where we are in the hierarchy. We are what's often called a field office. So we're kind of at the bottom of this hierarchy that consists of the National Oceanic and Atmospheric Administration. So we are a branch of NOAA, and we fit in the government's Department of Commerce. So our goal is really to provide information for the safety of people as they commute and as they go about their recreational activities and things of that nature. So across the nation, we have different regional offices that break up all of the different forecast offices local to that area, and they help to really synthesize all of the different weather events that are happening at each weather forecast office to provide a broader view to regional managers. So they'll be in contact with people like FEMA, and in some instances, they may be in contact with higher government officials that may be much more tied in with the federal government. So we have all of our regional offices. We are part of the Eastern region. And across the nation, we also have several national centers. Each of these national centers are specialized experts in various fields of weather. So the Space Weather Prediction Center, looking at things like those geomagnetic storms that come across the area that could produce things like aurora borealis. The Aviation Weather Center, which works with people like the FAA, as well as air traffic controllers to manage flights across the nation. The Storm Prediction Center are the experts when it comes to severe weather forecasting and being able to produce longer range predictions of things like tornadoes. And of course, the National Hurricane Center for anything out in the tropics. But there are also some centers for more national views, like the Weather Prediction Center and the Environmental Modeling Center. And of course, our oceans can't be forgotten with the Ocean Prediction Center. And finally, the Climate Prediction Center, I'll point out, their primary goal is to look at long-range model data in the time frame of 2 weeks to 3 months. They also do some stuff out beyond 3 months, but a lot of that's mostly a compilation of statistics. But they primarily forecast seasonal outlooks. So whenever you see here is NOAA's expectation for the coming winter or spring season, the Climate Prediction Center plays a large part in that. We have a lot of river basins across the United States, and so with that, each river forecast center commands forecasts of all the different rivers and lakes and streams in these local areas. We are part of the River Forecast Center. That's kind of hard to see. There's a blue box against this blue contour. So our River Forecast Center is located here in Taunton, Massachusetts. And so we often forecast a lot of what's happening with water way up in the sky. The River Forecast Center deals with all of the information of where does that water go as soon as it hits the ground, and how do we expect rivers to respond. So when we had all that flooding in July, we were in constant communication with the River Forecast Center to make sure that we had up-to-date products. And for any flood event that we experience, we are constantly on the phone with them, working on the latest forecast, adjusting our forecasts for rainfall, and seeing how that affects area rivers. And of course, there's us, the weather forecast offices, each of us consisting of several meteorologists, all focused on the local area and learning how each of the different climate, terrain, geographical features affect the regional weather. And we spend a lot of time studying, performing outreach for the region, and making sure that we serve the local communities as best as we can. So in addition to meteorologists, we also have a hydrologist, a senior service hydrologist. He goes out and works with people like the USGS with our river gauges, also responsible for things like the drought monitor, coordinating with that larger network. It's a very broad network of these groups that handle those. So he's in communication with them, and also how much liquid we have in our snowpack as it's relevant to our spring flooding. We have an information technology officer because we have a lot of information coming in. So they are responsible for maintaining the integrity of our systems and what's coming in locally, making sure that all of us on the floor have data to work with and that all of that data gets out to you. Electronic technicians are responsible for all of the different pieces of equipment that we have across northern New York and Vermont. They are almost out every single day taking care of the different weather stations that we have across the region and making sure our NOAA weather radio is working. And the administrative assistant, without who our office would not be able to function. The observation program leader, who manages all of the co-op observers that are in the area. So they look at the sighting and determine whether or not they can create a network that is a very intense kind of program, but it's critical to our understanding of the regional climate. So they organize and maintain that network. And then the electronic systems analyst that really encompasses a lot of the ET and IT type thing, as well as a lot of different policy things. And so here are some of the things that happen with us on a day-to-day basis. We really do a lot more than just forecast the weather in the area. We issue, of course, the watches, the warnings, and the advisories that you see. So whenever you see a winter storm warning or a watch, or a tornado warning, or a thunderstorm, a severe thunderstorm watch, those are things that are coming out of our office. Of course, that's more situational, but we also issue the public forecasts. Whether the sun is shining like it is today, or if there is active weather taking place, we provide public forecasts on a fairly regular basis. Aviation concerns. If you are in general aviation, then you have likely used some of the TAFs that we issue on a 4 times a day basis. We also dabble a little bit in hydrology. Fire weather forecasting is also important to our area. We have 2 examples here. Brooke is one of our fire weather focal points and does a lot with the different state and local officials as far as teaming up with them to make sure that our forecasts are going out to them and are useful to them, especially when it comes to relative humidity. We often have a struggle with having too high relative humidity when it comes to the early spring months, once all the snow melts. And then sometimes we'll have a meteorologist on site when we go out to prescribe burns. And so they'll take measurements on the field and relay that information to those who are assisting with the prescribed burn. We also do a ton of outreach events. We host locally tours in the office, especially for college students that are interested in learning about what we do. But we also have others that come in from time to time when we have events like an open house, which hasn't happened in quite some time here. We go to outreach events. We have 2 of our forecasters that we're demonstrating what happens when a dam break occurs. And of course, we have people going out and taking snow surveys. And we'll do damage surveys to assess the intensity of thunderstorms and provide using kind of an expert analysis from different regional studies on wind damage, and we will rate tornadoes based on that. We do climate services and data management. There are instances where if there's a hazmat incident, we will provide hyper-local forecasts for that area, sometimes on the scale of minutes as far as what's happening. And of course, we do a lot of research and training. We do a lot of administrative work. I would say a lot of my, even just 2 to 3 hours of my day might be spent just communicating with people over email, organizing events and things like that, so that I can do outreach events like this. So let's hop into what Skywarn is. Skywarn is a nearly 60-year-old program that trains people to recognize and report severe or hazardous weather to help meteorologists make life-saving decisions. This program initially began with amateur radio people in mind. They were the source group of how this got underway. And over time, it's expanded as we reach out to local communities to help you be able to report and recognize severe and hazardous weather to keep yourself safe as well. We really need spotters because a typical year will bring as much as 10,000 thunderstorms, thousands of floods, about 1,200 tornadoes. There's quite a bit of variability in that one though. Roughly 6 impacting hurricanes or tropical cyclones. And weather is responsible for roughly 500 deaths and 5,000 injuries per year in the United States. With about $15 billion in losses, weather events make up 98% of all presidentially declared disasters in the area. So again, amateur radio was where this really began, and since then it's expanded to emergency managers, first responders, media officials as well. And over time, it's begun to incorporate more researchers, students, members from the general public, co-op and COCO-RAs or storm chasers. The main theme of that is anyone can be a storm spotter. So why again do we need spotters? We have all kinds of fancy equipments and tools. We have technology that helps us know the weather without truly being out there, but we still really need that ground truth information of what you're seeing on the ground. Despite our surface observations, our upper air observations taken via balloons, computer models, our satellites and radar, they all still have their limitations. They're not quite perfect pieces of equipment. And so here I'm going to give you a few examples of this. Our ASOS, or automated surface observation systems, observe weather at a point and very high detail. There is things from wind sensors to ice accumulation sensors, present weather types, temperature, salometer, dew point, visibility, lightning detection, and precipitation. They cover a lot of different pieces of information, but they do so at one point. So they may be telling you what's happening right there at that sensor, but they may not be telling you exactly what's happening out here on this mountain that may have vastly different weather conditions from what's happening at that station. So while these provide a lot of important pieces of information, they're primarily used for things like aviation, as planes approach or as they take off. They rely a lot on this high fidelity data. But once you get beyond this point, the accuracy of it gradually decreases as you get further out from these type of systems. Another piece is weather radar. Weather radar is something that, as you can see through this video, will scan at varying angles as it makes 360-degree rotations. Being able to do those scans at different elevations helps it to capture sort of three-dimensional images of what's happening with precipitation and thunderstorms and things like that. Radar is critical to our ability to examine a storm. Using radar, when we see certain reflectivities at a certain height, say oftentimes that can happen, say this 6.2 degree tilt, when we see important pieces of information at these higher elevations that there's higher reflectivity out here, a lot of times that corresponds to areas where cloud ice is beginning to develop, which is critical for us to forecast things like thunderstorms. So when we see those high reflectivities at high elevations, that can help us get the jump on when a thunderstorm is ready to produce lightning. But radar is also useful for us to determine when weather becomes severe. However, this is why radar is not perfect and why we need spotters. The radar beam will be blocked by non-meteorological targets. So you can see in these images, let me change the color here to something that you can see against this black background. Yellow is usually a safe color. So you can see there's all these different artifacts that are just right to the east of the radar. A lot of that is things like buildings or some of those rolling hills. And right about here, you have the Green Mountains. So the Green Mountains act as they block the radar beam. And so as a result, you get nothing beyond that. And so then you have this broad region where the radar has a hard time seeing what exactly is happening. However, as you go higher up in elevation, you're able to see a little bit more about what's actually happening. However, this type of stuff, being 8,600 feet above the ground, is a challenge. We observe, of course, most of our weather and most of the important stuff that happens, like a thunderstorm rotating and producing a tornado, happen below 4,000 feet. So those kind of things, assessing supercells is hard when we can't see closer to the ground. And so that's why spotters are important. Radar might be looking high up in the cloud, but a spotter is able to look close to the ground and observe descending wall clouds. Based on your reports, when you provide information that's timely, when you give us key locations and things like that, we can match your report to what we're seeing on radar. And from that, we can take your report and issue warnings accordingly. We have a tag that says spotter verified. So your reports are important for us and add a level of validity to the warnings that we issue. Satellite is probably the single most important pieces of our technology. It helps us detect wildfires and their smoke. If you think back to our weather stations and how they forecast for one point, well, the satellite is able to take pictures of the Earth's radiation, and so it estimates the Earth's temperature. So it greatly expands the data that we have regarding the Earth's temperature. And of course, it monitors things like hurricanes, thunderstorms, incoming nor'easters, and things like that. Satellites really are hugely important to our field as meteorologists. But I would say they're the number one thing that's difficult with them is often the resolution. This is high-res imagery taken off of 1 minute data, but usually we have data on a 5-minute time scale. But even then, satellite isn't perfect. There are especially issues here where we are high enough in the latitudes that we have things like parallax errors that take place, where the satellite has a hard time adjusting for the Earth's curvature at our high latitudes, and so sometimes the placement of features are a little off. And of course, our weather balloon. This is another really fun piece of equipment. They've been used since about 1896. Across the country, there are about 100 different sites that send these up, measuring pressure, wind, moisture, and temperature with these little packages that they're called radiosondes. And so you can see here's the thing that measures the, this helps to measure pressure. This helps to measure the temperature and the dew point. And within this is a GPS system that helps track it. And so you can estimate the winds off of that. And so these spend about 2 hours up in the sky, going as high as 115,000 feet, drifting as far as 180 miles, since winds high up tend to go about 150 miles per hour. And so here's a neat little time-lapse image with a composite of a balloon traveling up the atmosphere. So you can see the changes in wind direction as it ascends up the atmosphere. But we only send these up twice a day, and they fall under the difficulties of being, again, released at one point, and they're at the mercy of the wind. So sometimes they might not totally be representative of our area if they go a little too far afield. But they're extremely useful for us forecasting freezing rain versus snow. We can look at warm noses based on the data that we get from them. Also, we can observe damaging downslope or gap winds by the characteristics of the data that we see. We can look at the potential for winds that are high up to make it down to the ground. In the case of our significant wind event in December 23rd of 2022, which also corresponded to blizzard conditions out in the St. Lawrence Valley. We can also use it to assess whether or not thunderstorms are possible. And so I have an example from the super outbreak in 2011 showing the favorable conditions for tornadoes just through that model sounding, or that observed sounding rather. So all of this information from all of these different sources, they do go into these not so primitive looking equations. Mainly they're named primitive because they're the kind of basis of how a lot of this works. And as you can see, there are a lot of D's for derivative. So there are a lot of advanced calculus type stuff that's going into these. And way back when, as weather forecasting was kind of getting its feet, in the early 1920s to 1940s, these were all done by hand. But for us, it's time consuming and impractical. Well, for them, it was time consuming and impractical as well for long range forecasting. So for us, it's best to conceptualize and simplify this information and let things like weather models take care of the heavy lifting as far as these mathematical calculations go. But this gives you a sense for the complexity that we work with. We're working with nonlinear, chaotic, dynamic environments with a lot of uncertainty and a lot of imprecisions as far as the math and the weather models and the information that they can ingest. These computers here are running about 5 quadrillion calculations every second to do these mathematical calculations. And so with that, we're able to provide the forecasts for the weather, and from that, we start setting up our baselines and things like that. So our day-to-day forecasts when it comes to the weather are going to be the fronts, highs and low pressures, things like cold snaps and heat waves. And climate is the baseline or the normal that helps us describe our weather conditions and where they are relative to those longer range features that happen on 20 to 40 year timescales. So a lot of that is planetary circulations, like the Earth's tilt back and forth from spring to summer to winter and fall, looking at things like recurrence and frequency, like how often does the Burlington area get 1 inch of rain in the summer or winter? Is it increasing or decreasing? You can think of the most basic understanding of climate change is observing how over time the values in your long-term change and adjust with each 20 to 40 year period. And so with that, you affect your normal values that affect flora and fauna, and that helps to provide a picture of that as we examine those different changes. Climate zones can be very tightly packed. As many are probably familiar in this area, our region has tons of hills and valleys, drainage basins and bowls that get cold at night. I like to pick on Saranac Lake for being a very particular climate, mainly at the airport there, the Adirondack Airport. But we're not the only ones that have to deal with this issue. For instance, the big island of Hawaii has 11 total climate zones, all just based on its proximity to the ocean here, its large volcanoes and mountains, just its beach environments, the different ways that wind flows into the region. Things like the mountains will block wind from flowing into those regions, and things like that as well. So all of these different terrain features usually play a role into deciding how many climate zones we have and our proximity to the ocean and the equator. With that to be said, the sun is the most important piece in this climate and weather puzzle. The sun's heat over the earth is how we get a bunch of warming here. The earth produces a little bit of heat of its own, but really we need heat from the sun to be able to enjoy the life that we have, but it also creates weather as we know it. And so the earth absorbs it and sends some of that radiation back out. And things like trees, buildings, clouds, oceans, mountains affect how different areas receive solar radiation. You can think of Earth's tilt as well, where the equator is almost always going to be receiving direct sunlight, whereas in the winter, we're going to be receiving sun at an oblique angle, especially in winter, and so we receive less warming in winter. That contrast in temperature is the key to how our global circulations are formed. And so near the equator, temperatures are roughly the same just because you have fairly constant solar heating no matter the time of year. So you tend to have the light winds known as the doldrums, but as you get up into the poles, you're going to have a lot more active weather with things like the westerlies. And so with that, you have features like the polar jet stream that will move from time to time based on the position of high or low pressure as well at the ground. You have your subtropical jet stream as well that lies between the interaction of rising and sinking air across the tropics. And so that temperature difference explains a lot of different features, like why in the summer months we tend to get very weak cold fronts that really barely change weather conditions, whereas in winter we might have a day in the 50s that rapidly plunges into the teens following a strong cold front. The difference in solar heating between the seasons is the reason why we have stronger fronts in winter. In winter, we might be in the single digits, and Florida might still be about 70 or 80, whereas in the summer, we might also be in the 80s, and Florida may be flirting more with 90s. So that temperature contrast is the key function to our weather. And so with that, the wind picks up and responds to that temperature difference and results in our more active weather pattern, especially here when we get into winter. And so as a result of things like temperature contrast, when we have our damaging wind events and our gusty winds across the area, that's going to be most common in the winter months. Strong wind gusts will become increasingly common, and so I have the number of times that we issue things like our heat advisories and high wind warnings during the time of year. And you can see really it ramps up in October, peaks in November, and then it starts to wind down a little bit as you get into the heart of winter, with a bit of a secondary peak as you head back into spring and starting to see some of those stronger temperature contrasts taking place again as we start to heat up once more. So once we have all of this, we have our weather data, we have all the things we use to forecast weather, we have statistics, and all of these different fancy tools and technology at our fingertips. And we bring this all together using forecasts, probabilistic data, using models and their different simulations of the atmospheric conditions and what they might do. It's our job here at the National Weather Service to filter all of this down to something that you can hopefully understand. And so quickly here, I'll discuss what forecasting the weather is like. Forecasting the weather, there's always going to be a little bit of uncertainty as far as details, especially when you get out 4 days in advance looking at low resolution data. I have a picture here of the Mona Lisa, accessed via public domain. They've all been corrupted in different ways. And so you can still see, like, yeah, that's still the Mona Lisa, but there's certain pictures that are kind of hard to discern. But you get the general concept, and you can see where there's agreement or disagreement between different features, and figure out a kind of a consensus between these models or these different pictures. When we get into 48 hours of time, then we're able to get into those really high resolution details. But that means we have to look at those minute details that help us determine what's reasonable for a forecast. So if you've ever asked yourself, why does the forecast change so drastically? Partly it's we have a lot more available information, but the other part of it is it's a lot easier to get a clearer picture of events, especially when we get within that 48-hour time frame or so. And so a lot of people will, well, maybe I shouldn't say a lot, but the few vocal people may say, well, your forecast was very different 2 days before. And sometimes we kind of think, would you rather us not change the forecast at all when we recognize that something is very wrong and not make those course corrections? We make these course adjustments because we think that this newer data is telling us more accurate things. Now, it's not always the case that newer data is better data, but more often than not, it will usually help. And just a brief look at what exactly does a 40% chance of rain mean. I'm sure you see a lot of those different things, whether you're seeing the forecast, and a lot of times you're like, okay, they're forecasting a 30% chance of rain, I'm good, there's not going to be any rain here today. Or you might look at 30% chance of rain and say, okay, it's a done deal, like we're absolutely going to get precipitation. Back in the day, it was a little more subjective between forecasters, and when we only had 1 or 2 of these larger weather models, but now we have large family of models that we call ensembles. And so like a musical orchestra, these weather models play their part in helping us depict the whole. So say, for example, if 4 of 10 models show precipitation, then we can say that there's a 40% chance of rain based on 4 of 10 models distinguishing precipitation in the area. And so the other key element that I like to remind people of is to also consider things like the time frame. Is that 40% chance of rain over 1 hour, or is it over 12 hours? Those kind of details can be important into the overall time resolution of those things. A 40% over 12 hours is very different from a 40% chance in 1 hour. So those are some small details that you can always think when you see what the 40% chance of rain means. The technology is still growing. Machine learning is going to be playing a part in the weather forecasts of tomorrow. There's experimental work being done on using things like neural networks and AI type forecasts. They use a lot of model data and look back to the past to forecast the chances of severe weather in the future. So they take previous forecasts and see what their observations of similar type patterns are in their correspondence with severe weather, and try and pinpoint the probability of severe weather. And so here I have a particularly active day that happened in January of 2023, where different models, where the neural network forecast was really highlighting a severe weather outbreak in parts of eastern Tennessee, northern Georgia, and along the southern Appalachians. And so with that, there's also a small increase here that I should point out off the coast as well. With that, let's see how this AI model did on this particular day. So as you can see, there still is a little bit of work to be done, but it is quite good at being able to capture some of the general trends of observing severe weather. They will likely run into similar hurdles as far as current weather models. You're only going to have a weather model as good as the input. So with imperfect inputs, you're going to get an imperfect forecast. But the type of data that AI will be able to tell us in the future will probably add another facet, another tool in the toolkit for weather forecasting. And so hopefully they can help us handle large forecast ranges like this. So if you were shown this, how would you handle the forecast if you had a varying weather models telling you anywhere between 2 and 4 inches, or telling you something more like 4 and 16 inches across each of the different towns across the area. What type of approach would you take? Things like that are things that we're doing as meteorologists. We are playing with statistics on the fly, using information like this to help us make quick and efficient decisions about whether our forecast is reasonable. And this was a storm last year where we were forecasting lower values from the statistics in terms of snow, anywhere between the 3-inch and on the higher end 10-inch mark. But as far as what was actually observed, it was really more in the 8 to 18-inch range. So if the forecasts had played more in the middle of these boxes, they may have stood a better chance of falling within the forecast that was observed, or the observations of snowfall that were observed on that day. All right, so at this time, feel free to put any questions that you have about Skywarn, about the National Weather Service in general, and anything else that comes to mind. I'll take a look here now at the questions that we have in the queue. All right, one of the questions here I have, in terms of complexity of microenvironments, how complex would this forecast area be? I think this forecast area is very complex. Usually our issue is the cold hollows, as we sometimes call them, those areas in higher terrain that have a little bit of a dip in them. These hollows tend to be favorite spots for cold air just to sink in. And sometimes it only takes as much as 30 feet of a dip down or to create these conditions. So places like the Adirondack Airport at Saranac Lake is probably our hardest area to forecast for, because if they do have any kind of cold drainage at night, we can see temperature forecasts that are off for that airport, sometimes as much as 10 to 15 degrees within the same day of a forecast. So the forecast is complex. We just try to do the best that we're able with representing, especially because we have to work in a 2.5 by 2.5 kilometer grid space. So there's no way that we could get everything, but we do the best we can. Does the National Weather Service Burlington have a recommended or sponsored local course program for learning about ham radio operation? We don't provide any ham radio operation courses here at the National Weather Service in Burlington. So I would check if you have any local radio clubs. I think there's plenty here in the North Country that I've seen. That there are several groups out there. What is a debris monitor, and how does it help monitor tornadoes? That'll be something that we get to a little bit later in the presentation. We'll talk a little bit about that debris that comes from a tornado. So we'll come back to that one. Are there any additional questions before we hop into a safety first kind of part of the presentation? All right, well, let's hop into talk a little bit about safety. So when dealing with hazardous weather, of course, I want to emphasize safety first. When we're dealing with hazardous weather from severe thunderstorms and things like that, we want to ensure your safety comes first. Be aware of the weather situation, whether or not we are expecting even just, I'll throw in a little bit of winter there since we're kind of still in the cold season. Be aware if we have winter storm watches or warnings out in place. Think about if there are thunderstorms expected between 4 p.m. and 6 p.m. that are going to be widespread and have damaging winds. Having that awareness and having communication methods to receive forecasts, whether that be through radio or your cell phones or weather.gov or the local broadcasts that we have in the region. Having that way to help yourself stay aware of the situation and communicate is helpful. And in advance, before these events take place, have escape routes and safety zones in mind, that if severe weather goes, if the weather goes foul in your area, that you're able to make a quick escape and reach your safety zone to ensure that you're protected from hazardous weather. So the most prominent example is, say hypothetically, we were forecasting a widespread tornado outbreak to occur here. It'd be best to have a day in advance, an idea of how you could get yourself to safety before the tornadoes take place, so that you can take the action that you need to confidently when the need arrives. So that's something that's important. Your safety is always number one. When it comes to reporting severe weather, never put yourself in harm's way to report severe weather to us. Typically, the best course of action is going to be to move away from windows and get indoors near the center of a sturdy interior structure. That's going to be the most common way that you can protect yourself from severe weather hazards. But in the case of flooding, sometimes that may cause you to move outside of a low-lying area. The biggest thing with flooding is to avoid rising creeks and water-covered roads. About 2/3 of all flood-related fatalities occur from people wading into floodwaters, whether that be walking or driving. So about 280 of those weather fatalities, remember we mentioned about the number of 500, so a little over half occur each year from any of these thunderstorm-related hazards. And with water, when it comes to flooding, never underestimate the power of water. Just 6 inches is capable of knocking over an adult. 12 inches, just a foot of water that's moving quickly, can carry away small cars. And when you get to about 18 inches or 24 inches, larger SUVs, vans, and trucks can also be taken away. We probably have a little bit more time before we get into heat, the peak of the summer months, but still, since it's the warm season presentation, we'll make mention that once we get into summer, that we'll be concerned about things like the heat index, which is a combined measurement of temperature and humidity that helps us to analyze the potential for heat risks. And so when we issue things like heat advisories for our region, locally 95 or higher for a couple hours, or if the excessive heat warning, when we have heat indices greater than 105 for at least 2 hours, that'll be the most important day to stay hydrated, have some place that you know you can get to that has a air conditioning working, and knowing what you can do as far as things like transportation, making sure you can keep yourself cool no matter where you need to go and where you need to be. So in those days, it's best to slow down, dress appropriately for the heat, have plenty of water for hydration, and practice good sun safety with sunscreen and things like that. Know the difference between things like heat exhaustion or heat stroke. Heat exhaustion, you'll still continue to sweat in the cases of heat exhaustion, but when you start getting to heat stroke, there will be no more sweating taking place. So when you make that critical turn, that's when you've moved to the need for medical attention. When you start feeling the effects of heat exhaustion, then that's when that's your time to seek cold shelter, find drinking water, and take a cool shower if need be. And so when we are messaging our hazards to keep you safe, we follow this kind of pyramid approach that kind of starts broadly and over time gets a little more concise in detail. Our outlooks, this will be issued in like 3 to 7 days especially. That'll be the time to check any action plans if we are calling for severe weather in our outlooks. The watches indicate that this is the time to monitor conditions for the latest forecasts. The weather hazard may not be there yet, but they are likely to materialize. And the warnings are when those weather ingredients have come together to make eminently severe weather. That's when it's time to take shelter, when you hear the warnings going off, so that in a matter of seconds that you can save lives by having that effective escape route and safety zone prepared beforehand in our outlook phase. When it comes to winter, things work a little bit differently as we have a little bit more time to assess the situation. With the outlooks, we really focus on the risks like the potential for travel impacts or power outages. And when we get to the watch phase, that's when we expect a winter storm capable of at least 7 inches or more of snow. And in the case of an ice storm watch, about a ½ inch of ice. This is issued with at least medium confidence. So if we're thinking about those statistics, something that say the weather models, their mean and median is about 50% in that 7-inch range. That's when we might start thinking like, all right, it's time to issue those winter storm watches. The warnings happen in the 0 to 2 day time frame, hopefully not in the 0, but generally we aim for about a day and a half in advance. And that's when it's time to complete any winter plans, whether or not you want to avoid travel, whether or not you want to have extra food, non-perishables and things like that. And these are issued once we have at least high confidence in the situation of exceeding 7 inches of snow. Now, high confidence is not total confidence. There are times in which we bust the forecast, but the idea is to really highlight potential. That's the biggest part of these warnings, to help you take any actions, to help you be focused in on the situation, to think about what you need to do to keep yourself safe. And when it comes to the day 0, when we are seeing the snowflakes flying, that's the time where you can monitor for any spots of particularly heavy traffic, checking your local 511, or whether or not you have any Facebook groups or any TV networks that you trust. As long as you have things like emergency kits and things like that prepared, making sure that you're ready for old man winter by having things like blankets in case the power goes out, having extra food, making sure that you're well stocked on any medications and things like that. That's when you've taken a look at things like our outlook and prepared during the watch and warning phase, then you're ready to comfortably ride out these winter storms when they take place. And so we are starting to move off of winter, but just as a reminder for all of our spotters out there, winter storms are when we expect 7 inches or more of snow or significant mixed precipitation. The ice storm is when we expect ice to be the primary issue with at least a ½ inch of ice accumulation. Blizzards are a threefold feature containing not just heavy snow, but also low visibilities less than a quarter mile, or sustained wind gusts or frequent gusts greater than 35. And the key part of a blizzard is that they last 3 or more hours. So blizzards have this criteria. They are known for their whiteout conditions, most recently experienced in the St. Lawrence Valley at the end of the year in 2022, where a long-lasting, nearly 24 to 36 hour blizzard took place, and the whiteout conditions there can easily cause someone to become disoriented and lost, especially in blizzards. We encourage people to ride out the storm and not try and go out in blizzard conditions. Extreme cold is issued when either wind chill or temperatures are expected to fall below 30 Fahrenheit. At that stage, you can get frostbite in as little as 5 to 15 minutes to exposed skin. High winds are issued when wind gusts get to 58 miles per hour or greater, or when there are frequent sustained gusts of 40 miles per hour or greater. One of the tools in your toolkit to help you stay safe in the outlook phase at the top of our pyramid is the graphical hazardous weather outlook. These are going to be color coded by each day over the next 6 days. And so you can get an advanced heads up on each of the different weather hazards for a day. And so in this particular case, I have highlighted one of the big cold air outbreaks from last year, where we had wind chills in the 30 to 40 below range. So you can see the color coding gets a little more intense for the more severe hazards, and it highlights each of these individual risks. So if you click each box, it will show you that risk on that map, and that is directly derived from the forecast that we provide. So this takes all of that information and assigns the values based on the threat risk potential. So green means no risk, and then as you see, you have the yellow, orange, red, and purple as you get to more extreme values. The Storm Prediction Center does something similar with their severe thunderstorm risk categories. So when we start talking about severe potential, we look to the Storm Prediction Center as they are the experts on severe weather forecasting. You'll notice that these are communicated in 3 different ways. One way is by color. Green is good, red and purple is bad. There is a number label as well, 1 indicating a low chance for severe weather, and a 5 indicating a high chance for severe weather. And then for those who prefer words and descriptors, you also have marginal, slight, enhanced, moderate, or high. So this graphic is specifically made to cater and make sure that everyone is able to understand based on the 3 different ways that you might be able to view severe weather hazards. And so on the green scale or level 1, you may have limited, isolated, short duration, low intensity severe thunderstorms. But at the moderate or high range, we might be talking about widespread, likely or expected, almost guaranteed severe weather that could be long-lived and particularly intense. And they graph these out on a map, and so you can use that to graphically find wherever your highest threat potential is, and they subdivide it in each of the different categories from tornado, wind, and hail, and you'll notice that they provide a small area. Sometimes they'll hatch these where a significant event is going to happen. So that would be more than just a severe thunderstorm, but we're talking like 2-inch hail, 70 to 80 mile per hour wind gusts and thunderstorms, or tornadoes that are likely to be long-lived and violent. Violent tornadoes being anything that is EF3 or greater. The watch versus the warning phase, we really like to emphasize this as this is one of the most easily misunderstood things that we issue each summer. The watch phase is kind of the heads up, here's the alert, start keeping an eye on the sky because conditions are favorable for severe weather development over the coming hours. So severe weather is probably not yet occurring, but that's the time when we say, hey, the conditions are just about here, start preparing for active weather in the region. When we get to the warning phase, severe weather is imminent or ongoing. So when we're talking about the warnings, the thunderstorms are about at your doorstep. You have about 15 to 45 minutes to take action when you start seeing things like the severe thunderstorm warnings. And so it's important to know the difference, that the watch is to be alert, the warning is to take action, because a watch is going to cover a large area. House 1 and 2 are both in the watch, but only House 1 may be in the part of a warning. So the watch is to show conditions are favorable, but the warning is really important for showing the imminent conditions. Is it possible over time that House 2 might get its own warning? Yes, but it's also possible that they get no thunderstorm that that could cause severe weather. The watch is mainly to show potential, and a warning may only be as far as 10 miles away from the doorstep. These methods of weather forecasting, especially for severe weather, is all about ingredients. So if you're an avid baker, then you'll be fond of this analogy. A cupcake watch might be issued when you have butter, flour, sugar, the cream, vanilla, eggs, everything that you need to make a cupcake present. And the warning is once you've put all these ingredients together and thrown them all in the oven such that you have now made your cupcake and applied your frosting. The cupcake is imminent and ready to be enjoyed. So whenever you have the ingredients present, the watch is issued. It hasn't yet come together, but that's the watch. When it has come together, when the time has come, the warning is what we issue. And I'll make one more distinction here between severe thunderstorm watches and tornado watches. The severe thunderstorm watch, look at the risk potential. If the tornado risk is moderate, it will always be a tornado watch. Even if another hazard is higher, as long as the tornado risk is moderate, it will always be a tornado watch. If the tornado potential is very low, then the severe thunderstorm watch is going to be issued, especially when all of these different other hazards are likely to be of greater significance. Here is the criteria for each of our different warnings. The severe thunderstorm warning is issued when thunderstorm wind gusts of 58 miles per hour or greater are expected. In general, it's hard for us with all of our forests and mountains to observe a 58 mile per hour wind gust. So we often issue it based on the expectation of downed trees or power lines. And then the other criteria is hail that is greater than 1 inch in diameter when measured from tip to tip. A tornado warning is issued whenever Doppler radar indicates strong rotation or when we receive spotter reports confirming a tornado, like this situation here in this photo taken in Middlebury, Vermont. Flash flood warnings are issued when we expect there to be fast-moving flowing water over roadways. So there's a river where there should not be a river. And so with those rapid rises, especially in things like ice jams that could threaten life and property, we issue things like flash flood warnings. And so all of our different warnings, they have a tiered impact-based system. And so if you ever have heard of our products and listened on the radio, usually more often than not, they'll just be the default. Severe thunderstorm warning issued and is in effect. Expect gusty winds, large hail, things like that. Now, when we say a storm is likely to produce considerable damage, that's when we issue these tags for winds, gusts of 70 miles per hour, golf ball sized hail, and things like that. Now, these don't trigger the wireless emergency alert system that will trigger on things like your phone, but the destructive category will. Destructive events especially are going to be life-threatening. They have wind gusts likely in excess of hurricane force and baseball-sized hail that can cause serious injury or even death when being struck by these falling hailstones. Wording gets greater with each of these different threats to life, and incorporated in these are not just severe thunderstorms, but also tornado warnings, flash flood warnings, and our snow squall system as well. So only during these major significant destructive events, when our wording is going to be the highest it can possibly be, will it alert the wireless emergency alert system such that the immediate actions to preserve life are taken in those highest end events. And so with all of the safety stuff and all the criteria taken care of, let's hop into the ingredients that make thunderstorms possible. At minimum, thunderstorms need these 3 things. Thunderstorms need 1, moisture, 2, atmospheric instability. There needs to be something to help air keep moving up. There needs to be some kind of forcing mechanism that helps to lift it up, a little less needed in the summertime. Usually number 3, this forcing mechanism comes from cold fronts and things like that. But it can also be even things like our mountains as well. To become severe, storms need a little something extra, and that something extra is wind shear. There are a variety of different combinations of moisture, instability, and forcing mechanisms that make storms more or less severe. Generally, the more organized, the greater the severe threat, and wind shear is what really helps to drive thunderstorm organization. I like to say the more photogenic a storm is, the more likely it is to be dangerous. So here's what wind shear is. Wind shear is just any change with the wind as you go higher and higher up Earth's atmosphere. There are 2 types. You have directional shear, which is ideal for supercells, and this is a change in wind direction. So winds might be going from southeast to northwest at the ground, but higher up at the altitudes of where jets are, it's going to be maybe more out of the west, headed to the east. This change in wind, you can see, makes it, this is how you get things like thunderstorms to rotate as air moves up. Now, directional or unidirectional shear, or just unidirectional shear or speed shear is just going to simply be wind coming from the same direction, but they are going to be increasing. So you might have a 5 mile an hour wind at the ground, but way up high where a plane is, it may be, say, 55 miles per hour. And so what this does is this causes this kind of rolling in the atmosphere. And so this is really important to driving things like shelf clouds that you might observe ahead of a thing like a squall line. Unidirectional shear is ideal for producing those long, big line of thunderstorms and producing things like straight line winds. And so when you bring that all together, think back to our cupcakes. Thunderstorm Development 101 is based on ingredients. You have the need for heating from the sun. And when you start to bring those ingredients together from things like cold fronts, bringing in moisture from either the Gulf of Mexico, the Atlantic Ocean, or the Great Lakes, when you bring these three things together, those are often the three things that we need to produce active weather here in the North Country. And so what exactly is thunder? Thunder is, it's a lightning bolt. As soon as that lightning bolt occurs and flashes, it heats the air that surrounds it. And so the cause of thunder is air is expanding as a result of that heat. And then once the flash of lightning has dissipated, that air begins to cool, causing it to contract very fast. And so you can think of air expanding and then coming right back together. That creates the name that we've given it, the thunderclap. Now, usually you hear the thunder over the distance of about 10 miles from the strike, but the longest strike that's ever been observed is 477 miles in length. So when we say thunder roars, go indoors. And if ever you have time, I might also recommend taking a look at this. This is a GIS story map that is how they measured the length of that lightning strike. A very deep dive into it. Even some of that goes a little over my head, but still a very neat little presentation if you have interest. So here's a slow motion of lightning taking place. So you have different charges, and so it's striving to make a connection with that opposite charge. And so you see all those little leaders that are coming ahead of the lightning strike. They're looking for that opposite charge. And once that connection is made, that is the moment that the lightning bolt strikes. So we'll let it play one more time. So here come the step leaders. Connection made, lightning strike. So that is the basics of how the lightning strike happens. Something that's quite neat and is becoming even just better understood even over the last several years. All right, we'll take here, let's give ourselves now, let's give ourselves a 5-minute break here. I'll come to the questions when we get ourselves off of this 5-minute break. Return at 8:08 and we will continue our presentation. So, 5-minute break here. All right, 5 minutes are up, so we'll return here to answer some of your questions. All right, so first answering here, should we be concerned about hazards posed by wildlife while trying to get these reports in? I think that's quite rare that these kind of instances happen. The only one that I can think of off the top of my head was one where a strong wind gust knocked a beehive on someone and injured them as a result of the bee stings. That's the only instance that can come to my head from a wildlife situation. Typically, I would think that if you're going to be in an interior structure while observing severe weather hazards, that hopefully you shouldn't encounter things like wildlife. But if you're out hiking, just kind of be aware of your surroundings as you'd be aware of the weather. During times of severe cold, does covering all skin include using a bandana to fully cover the face to help reduce the chance of frostbite in a major way? Generally, you're gonna want something a little bit thicker than a bandana, but you are still covering your skin to a certain degree. When it comes to just covering your skin and making sure it's not exposed, really anything can help, but you'll probably want some stronger fabrics than a thin bandana to help cover against the cold and the wind. What's the yearly amount of tornadoes the area receives normally in a year? The Vermont and northern New York area typically receives 1 or 2 tornadoes every other year. So it's usually not extremely common, but about every other year for the region. We have 2 similar questions. So a strike means when it hits something is the question, or what's the technical definition of a strike? So with this, lightning can also flash in the cloud as well. Whenever there is an in-cloud flash, we tend to call that a pulse. A strike is whenever there is a connection that is made with the ground. How we detect strikes is a means of triangulating. There are lightning detectors across the region, and as long as 3 of them pick that up, they can detect when lightning hits the ground. So when you have any of this electricity, this static charge that makes that connection with an opposite charge on the ground, such that you have that lightning flash that hits the ground, or really any building, anything that's connected to the ground, I suppose also counts. That is something that would fit the definition of a strike. And unfortunately, we also have a question here about the picture comparison of graupel, hail, or sleet. I know the picture you're talking about, but unfortunately I don't have it in this presentation. I'll quickly describe what graupel is. Graupel is it's a word that almost translates to soft hail. And so in some ways it's similar, but graupel is technically a type of snow. Graupel forms as a result of supercooled water. It's usually above freezing when graupel happens. And so as you have this water that's quickly ascending, so you need things like snow showers, like convective, usually they can happen in things like snow squalls, or when there's a big upper low in the area. And so that water is moving into this area where it's able to become ice, but may not have enough time to really form these dendrites. It tends to form these really dense, compact features as they descend to the surface that kind of has like a little conic shape, so it almost looks like a pyramid almost from an angle. And so it's technically snow, but it kind of sounds a little bit like hail because there's a little bit of ice involved in it too. Hail, it happens when you have your thunderstorm that's developing. Again, your water is moving into an area where it's super cooled and can become ice. And so what happens with hail, it cycles in and out of a thunderstorm over time and collects more water over time, such that you get this kind of ring of ice here. And then sleet happens when you have, say, a snowflake falling and encounters an area of above freezing air above the surface. And then when it gets close to the ground, it refreezes when the temperatures are below freezing before hitting the ground. So it's going from solid, liquid, back to solid before reaching the ground. And so it makes kind of a lot of pinging. So usually it's going to be very small, whereas hailstones are going to be large. And so with that, let's hop into climatology of thunderstorms, as we're kind of already running quick on time here. The brief overview here is that our summer months are going to be the most active weather with the most daytime heating and a moisture feed from the Gulf of Mexico. And unlike Florida, we still get fronts in the summer. So we make a quick ramp up. We can get severe weather as soon as April, but really it's May, June, July, and August with a rapid drop-off in September and October. We usually observe our severe weather between 1 p.m. and 10 p.m. for each of our severe weather hazards. You'll kind of notice there's probably a little bit of a discrepancy just on the fact that a lot of people are asleep between 0 and 7 or 8 a.m. So with that, we still do really need that daytime heating though to produce severe weather in our region, but generally occurring between 1 p.m. and 10 p.m. Our notable concentrations are going to be around our big population areas. So there's going to be a cluster around road areas and our higher population towns like Burlington and Plattsburgh and Middlebury and Rutland. Wind has a little bit less of a correspondence, especially if someone is outdoors hiking and things like that. They'll be able to tell us about down trees on hiking trails. So with that, there's a little bit of a less of a cluster around that area as a result. There's not much of a correlation between population and tornado reports. It's really more terrain influenced. So I'll just highlight here the St. Lawrence Valley and the Champlain Valley as being the primary areas. Mountains act to disrupt circulations. That's not to say you can't get a tornado out in the Adirondacks, but typically your valleys are going to create more conducive environments for tornadoes, as you won't have any things like the Green Mountains or the Adirondacks disrupting these circulations that develop. The Champlain Valley in particular is better designed for tornadoes in the sense that because of the Adirondack mountain range and the Green Mountain range, it's very easy for winds to funnel in the area from a southeast, south, or southwest direction, whereas the St. Lawrence is more geared to always be southwest. So with any high-end west wind event high up in the sky, it usually allows for a little bit more rotation within the Champlain Valley. So we use radar to detect signals from downburst wind to hail or supercells. It sends a pulse of energy out, and using these radar signatures, we look out for these different things on radar. We'll circle back to the question about debris balls. So radar looks at non-meteorological targets. It sees dust, debris, bugs, and things like that, and it sees it as highly reflective. So this area right here is probably not precipitation, but it's debris that's being lofted up as a result of the development of a tornado. So when we see things like the debris ball, that is almost a for sure indicator that a tornado is taking place. Other tools that we have beyond just radar reflectivity are tools from dual polarized the radar that we have with a horizontal and vertical beam that are sent out to see the characteristics of these events, and we use that to determine the distinction for telling these apart from rain signatures. So the radar, it sends that beam out and brings some of that is reflected back to the radar, and that's what we see. So the more reflection, the more raindrops, hail, or debris that there is. So with that greater intensity, storms are easier to pick up because we see a lot more reflected back. So it helps us to show the location, the movement, and the evolution of these systems. The single cell is left all alone. It's generally just an updraft that's isolated, but in some instances, the single cell can form into supercells, as I have here on the right. Multi-cell systems are clusters. They may be organized or amorphous in shape, kind of like a blob, but they're just several thunderstorms that are brought together with their main hazard being flash flooding. The squall line is the classic line of thunderstorms headed in the area, most known for straight line winds. And on the most extreme part of the spectrum, we have the derecho, known for its little vortex that we have here, as well as the strong thunderstorms with damaging winds that ride on the south side of that vortex. So squall lines can develop into derecho events, where you have these mesoscale convective systems. And so we use radar over time to watch how storms evolve. This is the May 4th, 2018 event, which was a high-end severe wind in our area. You can see the evolution of storms over time. And we use this to watch and determine where exactly severe weather is. So it starts as several single cell thunderstorms that eventually coalesce into a squall line as they head east into Vermont. The single cell thunderstorm, this is the life cycle of what a thunderstorm looks like. It begins with an updraft, usually on a nice warm day. Mountains often help to initiate. When a thunderstorm is matured, there's now a downdraft phase in which you start to see some of your rain falling. That rain helps to cool the air and ends up cutting off the warm updraft and ends up killing the thunderstorm. Kind of as this third picture shows, you can see the base is almost cut out from underneath it. So with no more warm air coming in, it's doomed to now dissipate. Now, sometimes the downdraft is strong enough to cause wind damage, and the most likely indicator of that, when you see the anvil cloud, keep an eye out for the overshooting top, where the updraft is vigorous enough to still break the stratosphere and ascend beyond that. That is usually your indicator for strong winds when you're looking at single cell thunderstorms. This is a visualization of what a downburst would look like. We can see these on radar. When wind hits the ground, it has nowhere to go but out. And so as a result, it kind of flattens everything or causes damage as winds gust across that region. They develop as dry air in trains and causes strong sinking cold air as it rushes down to the ground. And so here's a short video of what that looks like. So you can see just off this, just the trail of wind happening. So think of cold air and remember how dense it is. So a downdraft is going to lie very close to the ground and cause damaging winds flowing outward from the thunderstorm. I'll let that play one more time here. All right. Straight line winds, these happen from squall lines. The jargon term is quasi-linear convective system, are groups of thunderstorms that often accompanied with those high winds and occasionally tornadoes, but generally these can be hundreds of miles long, and so with their fast winds they can create more widespread areas of wind damage, like what was observed along this hillside. And then derechos take things a step further with having a handful of hurricane-force gusts that result in extensive areas of wind damage. And when that happens, they can be qualified as derechos. So for example, in this case, the Adirondacks had about 2 million acres worth of tree damage as a result of this particular event in 1995. Fortunately, derechos only come about every 1 to 4 years in this part. So I think there was recently one in 2022. So I don't think we're due for any for another couple of years. Hail formation, as we've noted before, starts with a warm updraft bringing water above the freezing layer such that it's able to start forming ice. But as it cycles in and out of a thunderstorm, it begins to grow such that if you were to cut a hailstone open, you could actually see the rings from it cycling in and out of this layer as it melts, refreezes, melts and refreezes and collects these new layers. So the longer time that hail spends in that area above freezing, the larger it's going to get. So a thunderstorm that lasts 30 minutes, less likely to produce hail. It's had very little time to cycle. If a thunderstorm has lasted for hours, then you've had more opportunity for hail to make that cycle and result in damage. As a result, supercells are going to be usually the things that produce hail. We see hail on radar by these different artifacts. Sometimes just simply called the hail spike helps us to see where hail is likely occurring. Supercells, their one distinguishing factor, the one thing that makes them different from any other thunderstorm is that they are rotating in the mid-levels. Due to that rotation, that separates the updraft and downdraft, and that lets them last longer and produce that very large hail as high as 2 to 4 inches in diameter. They're able to persist longer, especially in favorable environments, and 1 out of every 5 or 20% of supercells produce tornadoes. They're well known for their classic hook structure, but other features that correspond with them as the classic V-notch, where you have the defluence of these high reflectivity values out showing the high ventilation of these type of thunderstorms. They are known for their wall clouds. The wall cloud happens when you have the precipitation-free base. You have air flowing in and up along this area, and then you have air that's flowing out and down across this area, and that creates the favorable location for tornado development with the descending wall cloud in the area. So that is a very quick overview of the structure of a supercell. Be sure as spotters to know the difference between shelf clouds and wall clouds. A shelf cloud will cover the horizon. This occurs with squall lines, the straight line winds. That's when we're talking about a lot of speed shear. They expand over the horizon. They're really long and extensive. A wall cloud is going to be rotating. You're going to be seeing it spinning. These can be a precursor to a tornado. Not every time will they produce a tornado, but they'll be isolated lowering of the cloud bases. They will not span the entire horizon. They'll cover just a very small area. And here's an example of the shelf cloud, roll cloud again. They form as the large line of thunderstorms have their downdraft coming in behind it, and they're interacting with that warm inflow to create these horizontal rolls that provide these very fanciful images. Like I said, the more photogenic it is, the more likely it is to produce damaging winds as a result. And so you can see the very clear air behind the shelf cloud to the heavy rain that's just behind it. And of course, on a grander scale, you have tropical cyclones that are concentrated areas of thunderstorms over warm ocean waters that produce falling pressures that in the right environment become more organized. They need that warm ocean water, so as soon as they hit land, the greater friction and the lack of that warm ocean water that's their energy source causes them to rapidly decay. Now, with the warm rain processes, because they're tropical air masses, results in small drops. And in a 3D environment, the smaller your drop size, you can think of just how much more rain that is when you have these tiny drops and high rainfall rates. So flooding is the big issue with these. They can cause isolated tornadoes. Not very common here due to the way that tropical storms tend to track up the coastline. We probably won't be talking tornadoes with these. We'll mainly focus on flooding. In the interest of time, we're gonna keep going past this. I don't see any questions for now. We'll have a little more time for questions perhaps at the end. So let's talk tornadoes. Tornadoes are violently rotating columns of air in contact with the ground. As noted before, they're very rare, well, not very rare, but they are an uncommon occurrence. About one in every 2 years we'll have tornadoes in the region. And as long as it's not touching the ground, it's a funnel cloud. But once it is in contact with the ground, you'll see the evidence of it with debris being lofted up off of the ground, whether that be corn in a cornfield or tree leaves or any dust, bugs, things like that. As soon as you see something lofted, that is when your condensation funnel and your winds are affecting the surface. So until it makes contact, it is a funnel cloud. There are a lot of tornado lookalikes out there, so I want to provide a little bit of clarity on that. The rain shaft in thunderstorms can sometimes be mistaken, especially sometimes when the light hits it just right. It almost looks like there might be something right there, but really what's happening is you're seeing the edge of a downburst, and so all this rain is falling, and as this cold air is starting to hit the ground, it's kind of causing it to expand out and almost make it look like there might be something there. But really, this is just very heavy rainfall. Another situation that you might observe is scud, which is a type of convective debris cloud. And so with this, this was assumed to be a funnel cloud. We received this photo one day, but From this, it was difficult to evaluate really what exactly was happening, but we figured it was convective debris. You want to ask yourself things like, is it descending or is it moving up into the cloud? If it is moving up into the cloud, you're looking at an updraft where air is cooling and condensing quickly as it moves into the thunderstorm. You're looking at convective debris. So only if it's attached to the cloud and descending from a clearly defined feature like a wall cloud are we talking about funnel cloud. Anything else is more often than not going to be scud. When you're asking us to evaluate, we often need a little more than a photo to be able to distinguish these things. This photo alone is hard to determine what exactly is happening. It's really helpful for us to see videos and let us know when you took the photo, if you do send a photo or video. That really helps us match it to radar to be able to check these things. Weak tornadoes, the EF0s and the EF1s, comprise 80% of the tornado list. There are less than 5% of tornado deaths, so they're not usually particularly deadly. They have a lifespan of 1 to 15 minutes and usually are only go to about 3 miles with wind speeds of 65 to 109 miles per hour. Most of our tornadoes will fall in this range. The strong tornadoes, the EF2s and 3s, are about roughly 1/5 of all tornadoes, less than 30% of tornado deaths, lifetime 20 minutes or longer, with paths of 15 miles or more and wind speeds. You'll start noticing you're getting into the category 3 to category 5 part of hurricanes. So these can be quite destructive, strong tornadoes. And then the violent ones. I think earlier I said EF3 or greater, but I'll make a correction here. Just EF4s and 5s are considered violent tornadoes. These are 1% of all tornadoes and make up 70% of tornado deaths. Unfortunately, because the environment that creates them is usually very favorable, they also tend to be the ones that last the longest and can have paths in excess of 50 miles. Wind speeds of greater than 168 to 234 miles per hour will rip almost anything from their foundations. So with that, these are extremely destructive and life-threatening. And I think we can count ourselves fortunate in the North Country that we are unlikely to ever see anything like this. Let's quickly go over flooding. Flooding is caused by several factors that affect water moving in and out of a river. So if you're an engineer, the idea of inputs and outputs is probably something rather familiar to you. And you can think of water as these different balances of systems. You have tributaries, rain, snowmelt, and all this coming into a river and out of the river as ground infiltration, just the natural stream flow downriver, and the evaporation of that water. Flooding occurs when this gets out of balance, when the inputs are far greater than any of the outputs, such that your river begins to rise and overflow its banks. This can be gradual, which is usually how we designate flooding, or this can be very rapid, which we would designate as flash flooding. So the key difference is whether water rises rapidly in the case of a flash flood, or does water rise gradually in the case of a flood. Flash floods will be caused by excessive rain in a short window or things like ice jams. Floods will arise from gradual contributions. So left-hand side here, I have the Ausable, east branch of the Ausable, which is going to experience an ice jam any moment here that results in a rapid rise of the water. And there it goes. So you can see just how very quickly the water rose. This resulted in a record flood stage and caused significant damage at Ausable Forks. And on the right, I'll play this video here again, provided from the Vermont Agency of Transportation. We had a lot of rain on this April day in 2019. You can see some of the snow on the side of the hill here. So snowmelt and rain contributed to produce these rises along the river. I believe this is the White River, and it resulted in some flooding here along the roadside. Flooding is most common in the North Country through the months of May and August, just kind of like our severe weather season. Thunderstorms are going to tend to be localized, but in the instance of training, they'll produce the majority of our flash floods. And this graphic you can see here only goes to 2022, so it does not include all of the flash flooding in that happened in July in Vermont. So this is going to grow a lot higher once that is incorporated into this. But you'll see that there's some tails at the end of the season. So this will be ice jam season here. And then here you have precipitation occurring, but vegetation goes into dormancy in the fall, so they're not taking up that water. And sometimes you'll have tropical cyclones that roll in as well that help these kind of tails of the season, these little bumps here. But really the vast majority happening during the summertime from training thunderstorms. Well, when you see floodwaters, never underestimate the power of water, and do not traverse a road if you can't see what's underneath those waters. You never know what's happening underneath. So you have this culvert that blew out, and with it, the road eventually washed out as well. About 2/3 of deaths from flood-related deaths are from driving into floodwaters. So when we say turn around, don't drown, we really mean it. So briefly here, we'll discuss forecasting on the winds on Lake Champlain. It's all about mixing potential. There's less friction over the open water compared to the trees and mountains and buildings that cover much of the landscape. And water temperatures work much differently from the air. They are much slower to respond than air temperature. So oftentimes, as we are dealing with the fall and winter months, you have a lot of cold air rushing in, but the water's still warm from the summer heating, which makes the conditions unstable and means faster winds. We have channeled flow, mostly in the Champlain Valley, but to a lesser degree, the St. Lawrence Valley as well. This channeled flow happens as a result of the topography. This is a wind rose, which shows each ring shows the percentage value. So this shows that this is the Colchester Reef Place. This is the 20% ring. So 20% of all observed winds, and this includes like north-northwest, west-northwest, south-southeast, all of those. So of all of these different wind directions, 20% from the south-southwest, and almost 15 from the south. So winds are channeled between the Adirondacks on our west and the Greens on the east. And the St. Lawrence Valley doesn't have quite as much of a strong signal. There's a much bigger gap between the mountains to the west that lie in the Canadian plateaus there. But as far as our area, we have a much better chance for channeled flow here in the Champlain Valley. Now, in the winter months and the fall months, our winds are going to be unstable just due to cold air versus the relatively warmer water temperatures. But in spring and summer, winds become stable as the water temperatures only slowly heat up and result in weak winds. So here, just to kind of show each of the different seasons, you can see how quickly it ramps up from fall and then drops off as we head from winter and into spring. So really, once we start getting into April and September, it'll be time to enjoy our boating stuff. So before we get into reporting methods and a summary of everything we've kind of talked about here, I'm going to quickly see and pause here and see if anyone has any questions. All right, nothing seen. So let's go on to how to report information and how you can contact us. You can contact us. Our spotter network, we have a spotter line designated, so you can contact us by phone, by social media. Now, we might be very busy. It may be, we might not be able to check Facebook and Twitter 24/7 in highly active events. We have our amateur radio. We have a small ham shack that we have tuned to the whiteface repeater. So recently we picked up several of our storm reports for this last snowfall event. We had one of our forecasters listening in on the WeatherNet. So if you are a licensed operator, we will often be tuning in on that. And if you participate in that net, we might be hearing your reports there. We have a storm report page. We have a special designated page for that, and there is an app for that too. If you go to the iPhone or Google Store, if you download the MPing app, you can select your weather observations using the location data on your phone. And we enjoy when we see your photos. They help us to lay eyes on what you're seeing and help provide several expert eyes on the type of weather you might report. That weather includes funnel clouds and wall clouds. Once you see a tornado or water spout on the ground, of course. If you have very heavy rainfall in excess of 1 inch per hour, if you have hail, damaging winds such that you have downed trees or power lines especially, if you're observing flooding taking place when you have water on the road, or if something is shut down due to flooding, letting us know and letting the proper authorities know ahead of time. I would contact them before contacting us, such that they can close the roads in an orderly fashion. That stuff is important to report to anyone as well. Of course, we also greatly covet snow reports. I see a few of our St. Lawrence Valley people in here, and we have greatly appreciated your contributions from the St. Lawrence Valley as of late with our snowfall reports. So thanks a bunch for the work that you do there. And we encourage that from everyone. We really value your snowfall reports to help create maps that show elevation dependencies in our various microclimates. And then lastly, the other thing to report when it comes to severe weather is whether or not any injuries or deaths took place. And then the other big thing is to tell us when and who you are. Not all of us know all of our spotters, and sometimes our spotters contact us on an infrequent basis, so sometimes we might forget who you are as well. So letting us know who you are and when you observe these things are critical to reporting to us. When you're reporting hail, measure from tip to tip and do it fast. That hail is melting. And if you ever have anything that's greater than 3 1/4 inch diameter, especially take a photo to back that up, because 3 1/4 inch diameter is the record hailstone in our forecast area. So the record hailstone for our forecast area was taken, in fact, in one of our employees' own backyards. So that's always a fun thing. No matter how misshapen it is, measure from either end of the tips here. So here you go. You can tell I never went to an art class. And so all of the reports that you give us, they are vital to us being able to form our maps, especially when it comes to ice accumulation. Not every weather sensor is equipped with sensors to measure freezing rain accumulation. So we really, really, really appreciate when spotters give us ice information. Of course, I also have one of our recent snowfall events here where there was a lot of terrain dependencies here. You can see the Champlain Valley and St. Lawrence Valley stick out quite differently compared to the Adirondacks and the areas east of the Green Mountains. Spotter reports help to shape and put greater definition to these maps. And our severe storm reports, we highlight those as well. And also I've gotten in the habit of, if you've ever watched around December, I post a yearly summary and show the different ways in which Skywarn spotters help to contribute to severe weather. And I was just thinking maybe I can also start applying this more broadly, not just to severe weather, but also to winter weather events. So we greatly appreciate your help in helping us understand and track the weather in our region. It's really important for us to be able to document all of these different events and to understand the ways in which all of these different storms impact you. MPing, I'll just go over this very briefly. This uses the information that you input on your phone and maps all of the different reports almost in real time, such that we can see distinctions between rain versus areas where there's freezing rain and the thin line of just that thin and very quick transition as you get to wherever snow is taking place. So MPing really helps us measure out where sleet and freezing rain versus rain and snow can be occurring when we're dealing with these very tricky situations. So If you're comfortable with those type of location services being used on your phone, we usually are looking in IMPing to look for any precipitation changes like we recently had where we were closely watching southern Vermont for any intrusions of sleet and freezing rain. Make sure you have a lot of different ways to get alerts, whether that be via NOAA weather radio, alerts through your phone. If you have your wireless emergency alert system not turned off, you will get those WIA alerts. And have a local TV broadcast and media outlet that you trust. Have multiple ways to get alerts. If need be, use things like social media, friends and family. There are even things like VT alerts, which are email messaging services, and they will relay a lot of our warning products. Have the location where you're at marked on weather.gov, and if you have things like trusted apps and things like that, you can use those too. We've mostly focused on Skywarn, but if you're interested in more dedicated and involved things, we have the COCO RAS and co-op program, which help to build our climate data networks. They're a lot more involved as a result, and their citing is important. Skywarn, and on the whole, is a volunteer network that mainly focuses on observing and reporting severe weather as it happens. And so it's as often as desired and wherever you might be located. So those are some of the distinctions. And if you are interested in something more involved like COCO RAS and co-op, you can always let us know, and I'll be happy to pass that information along. I have below a list of some of those contacts for who you can reach out to for these different programs. So in summary, a reliable Skywarn spotter provides ground truth and potentially life-saving information, whether that be down trees or lines, where funnel clouds are occurring, heavy rain or wind damage is taking place as well. We rely on good spotters, especially because in this day and age, we have a lot of people trying to pass fake photos as legitimate reports. And so when we really know our spotter base in our community, it really helps us to trust and know that important ground truth information for which we have fancy tools, but they all have their limits. So having a good network of people who can report severe weather and relay that information to us is critical. It's very important. Storms come in all kinds of different shapes and sizes. The more organized, the more likely to be severe. If you look for like a lot of different shapes and things like that, usually the more photogenic, the more kind of organized it is and less blobular, the more likely it is to produce severe weather. So be on the lookout for lines or bow echoes, wall clouds, shelf clouds, and overshooting tops and thunderstorms when looking out for severe weather. Our most common time for severe weather is June, July, August. So we still got a ways to go, but I'm glad you're here to prepare for the summer season as we get closer. Remember, as we get to that time, your safety should come first, and never to put yourself in harm's way to provide us information. And when you are relaying those reports, be as specific as possible. We may not be familiar with your roads and cities, so it's really important to reference nearby intersections, landmarks, or even provide your latitude and longitude points to help us pinpoint where that is in relation to radar and issuing the warnings that we have. All right, so I'll get to some more questions here in just a second here. Before everyone starts hopping off here though, I want to say thanks for your attendance. Feel free to contact me at robert.d.haynes@noaa.gov. That .d is important because there's another Robert Haynes in NOAA. So if you fail to put that in, you will be sending your emails to someone else. So that is my contact. And if you'd like to become a spotter, feel free to email me, or you can even call the office to inform us that you've completed the course. And we'll give you that unlisted spotter information again. We just ask if you could provide a name and address, since most people report from home, or if you're not comfortable with that, you can always provide a latitude and longitude point. And a phone number. Sometimes we do cold calls, and so we're looking for that ground truth information. So there is a small chance, unless you state that you do not want us calling you. If you provide us your number, then we might end up giving you a call asking about some of the severe weather that you've observed. One of our forecasters recently went on a hunt
for reports in the St. Lawrence Valley for lake effect snow. And so that was really helpful to be able to help map that out. And that's just kind of one of the instances with which that can take place. I will say it is really rare. I would almost never expect a call from us. I once called a spotter, and they'd mentioned that they'd been in our network for nearly 20 years and had never gotten a call until I made one a few years back. So it'd be a very rare instance. All right. So here we go. Here's some of our last questions that we have here. What about microburst storms? Microbursts they're the same as a downburst. They're just a smaller scale wind event than, say, straight line wind events that correspond to squall lines. So microbursts, often we kind of elevate it from downburst to microburst, especially when it's a really high end event. One of the big events that I can think of in recent memory was a couple years ago now in August. There was a microburst that took place near the town of Mariah in New York that caused significant damage across the region. What is the preferred increments on a ruler yardstick for measuring snow on a snowboard? Generally, the preferred increments, you want to be able to measure snow in every 1/10 of an inch. And so with that, we're able to measure that to get the most accurate. You add that layer of uncertainty in that significant digit. It's a whole thing to go into, which I don't think we have enough time in this warm season workshop to go into. I'd also hope to go maybe a little bit into the eclipse excitement, but I don't think we're going to have time for that tonight. But generally, rulers or yardsticks to the nearest 1/10 of an inch is ideal. If we are already a spotter, do we need to provide that information again? Thank you. I've started getting the habit of knowing who our frequent spotters are by kind of marking the days in which we last interacted with any of our spotters. So with that, if there are any spotters that are already on this list, in fact, I recognize several of the names here tonight, I'll kind of mark that attendance, and that helps me keep track of who our frequent and reliable spotters are. So you don't need to do anything if you're already a spotter. I just appreciate your attendance and your interest and wanting to make sure that you stay fresh when it comes to weather information. So thanks for coming. All right, do we have any other questions out there? Not seeing anything at the moment. I'll hang on for another minute or two as just to see if there are not any more last minute questions. I know sometimes there can be a little bit of an audio lag between these type of things and when you start hearing me chatting again. So again, thanks everyone for your attendance this evening. I hope you enjoyed this presentation and found it useful. Again, we'll have it on our YouTube channel at some point with whatever the best recording is for this. Let me know. Feel free to contact me if there's any way that I can help you out. Always would be glad to do so. Thanks so much for your attendance. Apologies for going a little bit on the long side this evening. Perhaps I need to start booking these classes for 2 hours as opposed to 1.5 hours. Is there a way to get a spotter card that has this office's info and not another's? We don't mail out spotter cards anymore. We used to have like a thing that we would just mail out, but we don't do that any longer, mainly just for the sake of just the cost of doing that type of stuff for so many people was ballooning. So as a result, we kind of stopped that. There is the best contact info. Say if you just want to do like a screen capture of the reporting methods to have that contact information available. Also, I guess I don't highlight here, on weather.gov/btv/Skywarn, you have, I think I can even, I might be able to put it in this chat window here. Yep, and it recognizes the URL. So if you go to that page, it'll have a lot of this same information on there. I I upload PDF-friendly versions of these slides as well that has that contact information available. So if you always want to come back to that screen and bookmark the different URLs, you can do that there as well. Also, I'd like to highlight that we recently constructed a GIS story map that contains a lot of pieces of these presentations and a little bit of other extra things and details in there as well that are stored there in that Skywarn page that you can also peruse as well. And I think it should also even have some of these different reporting methods listed in that story map too. I don't need a mailed out version, just a print one. Maybe I could do that. I think that's something I could reasonably do. So I'll make that a task for myself to do here over the next few days to make a printout version. I can do that for you. That's a good suggestion. I'll write that down. Yes, I will probably take any printout spotter card and put it on the Skywarn page. That's probably where I will do it. Asked about the snowboard because I was one of the spotters you guys called, but I wasn't able to accurately give the info. I was also on the road. Do you mean as far as like asking about the snowboard is in just taking any measurements outside of the snowboard, or you just don't have any snowboard and are technically like kind of measuring off of a lawn or something like that? Oh, the increments. So in general, what we kind of do with that, I mean, realistically, when we have these big events where we're getting tons and tons of social media reports, a lot of people will just measure it to the nearest ½ inch. And we just kind of take those measurements just on the principle of just the fact that most people will have a stake in the ground or something like that. And so as a result, most people are technically measuring their snow depth and not their snowfall. So usually we kind of take a lot of those reports, even if they're not necessarily taken on a snowboard or have like a ruler that is increments of 1/10 of an inch. It just kind of depends. Ideally, we would like those rulers to be in 1/10 of an inch. I think there are like a handful of sites, like the Coco Raws is going to have a lot more of that specialized equipment because part of Coco Raws is measuring things like snow. But oftentimes we take measurements that are taken with equipment that is just measured every inch or ½ inch, just because we know that people are mainly limited to those type of things. I have heard it's hard to find measuring sticks than just 1/10 of an inch. I have heard it's a challenge. We're kind of spoiled with our observation program lead here, is he has all of those rulers that have that, and I think on the Coco Raws page it lists that type of ruler, and I think it goes up to 3 feet. So most snowstorms aren't going to create more than 3 feet of snow on an average event. All right, we are coming up on 9 o'clock. We are already almost 30 minutes past the time I budgeted, so I think this makes it as good a time as any to call it here. Thanks so much for your questions and your participation. Thanks so much for listening and joining in. Again, I hope you enjoyed the presentation. Thanks and have a great night, everyone.